Okay, so clock is still not working for us. It is 11 o'clock, time for us to start. Today we're going to finish our discussion of chapter 17. We're going to talk about types of aromatic compounds. There are several types. And then we're going to talk about the basis for Huckel's rule. Huckel's rule is the name for the 4n plus 2 rule. So we're going to explain why compounds that have 4n plus 2 pi electrons are extra stable. And then we're going to start chapter 18, reactions of aromatic compounds. While they are more stable than other types of compounds, they do still react. And we're going to discuss their reactions, the main reaction of which is called electrophilic aromatic substitution. So, types of aromatic compounds. The first ones we'll talk about are monocyclic aromatic compounds. Those are known generally as annulenes. So, benzene could be referred to as an annuline. And with an annuline, you put the number of carbons in the ring in brackets in front of the name. And that corresponds both to the number of carbons in the ring and to the number of pi electrons that you have, right? Because you have a p orbital on each carbon. It's fully conjugated. So we see here 14 annuline and 18 annuline. Those are both aromatic compounds. You could call benzene 6 annuline if you wanted to. You'll notice I've drawn 10 annuline for you on the board. But I've indicated that 10 annuline is not aromatic. Why is 10 annuline not aromatic? Think about the rules, the criteria for aromaticity. Why is it not aromatic? Yes, please, in the back. Okay, how many pi electrons do we have? In 10 annuline. We have 10, right? So it does fit. N would be 2, and it would have 10. So it must be another one of the criteria that it doesn't meet, yes? Okay, this molecule is not planar. What would happen if it were planar? Okay, we have hydrogens on these carbons that would be in the same plane, clashing with each other. There's not enough room for us to have these two hydrogens in the same plane. And so this molecule will twist out of planarity because of that. And so 10 annuline is not planar and therefore is not aromatic. But all other annulines that could be aromatic, that fit the 4n plus 2 pattern, will be planar and are indeed aromatic. It's only 10 annuline that has this particular problem with steric strain. Okay? So these are monocyclic aromatics. We mentioned on Monday that we can also have polycyclic aromatic hydrocarbons. We showed you benzoapyrene. That is the carcinogenic compound that's present in tobacco smoke and also in charcoal fumes. Here are some other polycyclic aromatic hydrocarbons that I've drawn for you on the board. Naphthalene. How many pi electrons in naphthalene? There's 10. Okay, so that fits our 4n plus 2 pattern. Okay. And notice we don't have hydrogens on these two carbons. We have a bond connecting these two carbons, so we don't have the steric strain problem we do in 10 annuline. Anthracene, how many pi electrons there? 14. That still fits our 4n plus 2 pattern. Okay. How many pi electrons in phenanthrene? Okay, it also has 14. It also has 3 rings like anthracene. And it also has 14 pi electrons. Okay. When we measure the resonance energy of these 3 molecules, we see something interesting. So the resonance energy for naphthalene is 61 kcals per mole. The resonance energy for anthracene is 83 kcals per mole. And then the resonance energy for phenanthrene is 91 kcals per mole. If you remember on Monday, we taught you that the resonance energy for benzene was 36 kcals per mole. So what we notice is that the resonance energy for naphthalene is less than twice the resonance energy of benzene. The resonance energy for anthracene and phenanthrene is less than 3 times the resonance energy of benzene. Okay? So the amount of resonance energy per ring is less for these molecules than it is for benzene. So what we learn is that aromaticity is kind of a sliding scale. Right? All aromatic compounds have these large values for resonance energy, but not all aromatic compounds are stabilized equally due to resonance energy. So these polycyclic aromatic hydrocarbons are not stabilized by aromaticity to the same degree that benzene is. So you could say they're aromatic, but not as aromatic as benzene. That would be one way to say it. So why is this? We can understand it by looking at resonance structures. So we'll do this with naphthalene, and I'll draw the resonance structure for naphthalene that I drew for you over here. And if you look at each of the 2 rings individually in naphthalene, you'll see that they both look like a benzene ring. However, if we move the pi electrons around in the left-hand ring, it's still cyclic, it's still fully conjugated, but now if we look at just the right-hand ring, it doesn't look like a benzene ring. When we look at the right-hand ring by itself, we don't have a double bond connecting these 2 carbons. So if we separated the rings and looked at them individually, in this resonance structure, the right-hand ring doesn't look like a benzene. The left-hand ring still does. We can draw a third resonance structure of naphthalene, where we move the electrons around both rings in this fashion. And now what we find is that the left-hand ring doesn't look like a benzene ring. Okay? So in these polycyclic aromatic hydrocarbons, we have one or more resonance structure that doesn't, where an individual ring does not look like a benzene. And that's reflected in the fact that the resonance energy is less than twice the value for benzene. Okay? If we look at anthracene, anthracene doesn't have any resonance structures where all 3 of its rings look like a benzene. Okay? Phenanthrene does. I've drawn the one for you here that has where all 3 of the rings look like benzenes. But there are resonance structures we could draw for phenanthrene similar to naphthalene where individual rings would not look like a benzene ring. Okay? So you can also, so in addition to noticing that the resonance energies for these molecules are less than either twice that of benzene or 3 times that of benzene, we also see that anthracene has less resonance energy than phenanthrene does, and that can be attributed to the fact that phenanthrene has one resonance structure where all 3 rings look like benzene, whereas anthracene does not. Okay? Any questions about that? So why does this matter? What are the practical consequences of this? Well, aromaticity causes stability, and it makes these molecules less reactive. So if we have a molecule that has less resonance energy, that's less stabilized by aromaticity than another one, we would expect it to be more reactive. So in fact, these polycyclic aromatic hydrocarbons will undergo some reactions that benzene will not. So here's an example. It is very, very, very difficult to hydrogenate benzene. You have to use forcing conditions to reduce the double bonds of benzene by hydrogenation because of its high resonance energy. Phenanthrene, on the other hand, has less resonance energy per ring. And this is a reaction we performed in my lab 15 years ago now, where we performed a hydrogenation of this substituted phenanthrene derivative. And you find that the central ring is the most reactive. The central ring was reduced with hydrogen, right? The hydrogen went here, leaving us a product with 2 intact benzene rings. But we lost the aromaticity in the middle because of the reduction. Okay? If you use palladium, carbon, and hydrogen, you would not be able to reduce benzene. It would just sit there. Okay? So these polycyclic aromatic hydrocarbons are more reactive than benzene itself. Even though they have large values for resonance energy, it's less per individual ring than that of benzene. So that makes them a bit more reactive than benzene itself. Okay? And you'll notice by reducing the central ring in our product, we now have 2 benzene rings that always look like benzene, that each would have that 36 kcals per mole of resonance energy. So if you look at the resonance energy for phenanthrene, you'll see that we've lost about 19 kcals per mole of resonance energy. So not too bad. Okay? Questions about polycyclic aromatic hydrocarbons? Yes, Brady.
Like then every single carbon would be conjugated at that point. So what makes that more unstable than aromatic?
Makes what more unstable?
So like on the phenanthrene, if
Yep.
every single carbon was conjugated, because right now there's wait.
In the phenanthrene, they're all conjugated. Yeah. Right. And here, technically, these benzenes are conjugated to each other because they're connected. Right, but they're not. They're each individual aromatic rings, right? You wouldn't say the whole thing is aromatic as one aromatic system because it's not totally cyclic because of that. Okay, yeah. So these are both aromatic. They're different aromatic systems. All right. So we can also have charged species that are aromatic cations and aromatic anions. One of our most common aromatic ions is the cyclopentadienyl anion. This is cyclopentadiene. The cyclopentadienyl anion has a negative charge. So normally if we had a carbanion, we would say, okay, that negative charge is going to be in a hybrid orbital. In this case, if this carbon is sp2 hybridized, and we put this lone pair in a p orbital, we now have 6 pi electrons. We would have a cyclic fully conjugated system if this is sp2 hybridized. Every carbon in the ring is sp2 hybridized. Each p orbital is going to overlap with 2 adjacent p orbitals. This is aromatic. It's called the cyclopentadienyl anion. CP is our abbreviation for cyclopentadienyl, and then we would put a negative charge here, indicating that is our cyclopentadienyl anion. Okay, 6 pi electrons. Here they're spread out across 5 atoms instead of 6 atoms, but nonetheless still aromatic. What about cyclopentadienyl cation? What do we think about this structure? How many pi electrons? 4. So does this exist? No, that does not exist. That would be anti-aromatic because it would have 4n pi electrons. So we can't make the cyclopentadienyl cation because that would be highly unstable. But we can make cyclopentadienyl anion. And then we could also have a cyclopentadienyl radical. How many pi electrons are there in this radical? 5, okay? So you'll notice that that's neither aromatic nor anti-aromatic. That's in between. So this would be non-aromatic. It would be stabilized by conjugation. Right? So it would not have the very, very high levels of resonance energy that you would have for an aromatic species. But because this is a resonance stabilized radical, we could draw 2 other resonance structures of this radical. Due to the conjugation, this is a stabilized radical, but it is not aromatic. Okay? So cyclopentadienyl anion, aromatic. Cyclopentadienyl cation does not exist, anti-aromatic. Cyclopentadienyl radical does exist, but it is non-aromatic. It is just resonance stabilized. So since cyclopentadienyl anion is aromatic, its conjugate acid is the most acidic hydrocarbon that we've encountered in the class. Okay? So this is cyclopentadiene. If we react cyclopentadiene with a base, we will deprotonate, and we will generate cyclopentadienyl anion. Okay? We've learned that any structural feature that stabilizes the conjugate base makes the acid more acidic. This conjugate base is stabilized by aromaticity. And so that makes the acid more acidic than any other hydrocarbon, any other molecule with just carbons and hydrogens present. So the pKa of cyclopentadiene is 15. Until now, the most acidic hydrocarbons we had encountered were terminal alkynes, acetylene or other terminal alkynes. Just for reference, the pKa of those alkynes is 25. We would need sodium amide, NaNH2, or sodium hydride to deprotonate a terminal alkyne. Cyclopentadiene is 10 orders of magnitude more acidic than an alkyne. It's still a weak acid, but 10 orders of magnitude more acidic than an alkyne because its conjugate base is significantly more stable due to the aromaticity. So this means that a base like potassium tert butoxide is able to completely deprotonate cyclopentadiene. Okay, question? Aryl and vinyl hydrogens would be very similar, yes. Because the conjugate base is stabilized by aromaticity. That overpowers the hybridization effect. So if you just looked at this molecule and thought about the hybridization effect, you would say, okay, we want the negative charge in an orbital with more S character, and so we want to deprotonate on the alkene. But we have aromaticity here. We have to consider the aromaticity. If we deprotonate this sp3 hybridized carbon, we get an aromatic conjugate base. If we deprotonate one of the sp2 hybridized carbons, we do not get an aromatic conjugate base. So the aromaticity here, that massive amount of stability, that resonance energy, means that we're going to deprotonate here to generate our aromatic conjugate base, and we will have a much lower pKa than in any other hydrocarbon. Okay? Other questions? So this anion is stable enough that we can make salts of cyclopentadienyl anion. We can pair it up with cations and end up with stabilized molecules. The most common one is known as ferrocene. So this is often how we draw cyclopentadienyl anion. We have that circle in the middle. We showed you that with benzene in our last recorded lecture as well as a way we can draw benzene. So if we have an iron 2 cation sandwiched between two cyclopentadienyl rings, this salt is known as ferrocene. Okay, it's a solid. It's a red solid because of the color of the iron. And the cyclopentadienyl rings will react in the same sorts of reactions that benzenes will. They'll undergo electrophilic aromatic substitutions, the types of reactions we're going to start talking about at the end of class today. So I'm not sure if the Chem 354 lab curriculum has changed, but it used to be that you would perform an electrophilic aromatic substitution reaction of ferrocene. So you'll perhaps find out. I'm not sure. I know with the semester being shortened, the curriculum for that class is a little different now than it usually is. But these rings behave similar to benzene rings in terms of the reactions they undergo, indicative of the fact that they are aromatic. Okay? So in addition to aromatic anions, we do have aromatic cations. Of course, not the cyclopentadienyl cation. We know that would be anti-aromatic, so that is unstable. However, this cation, which is known as the tropylium ion, it's a 7-membered ring. Okay. This is aromatic. How many pi electrons? 6. 6 pi electrons spread out across 7 atoms in this case. We know that carbocations are sp2 hybridized, so we have an empty p orbital here. So that means 6 pi electrons. That means it's cyclic, it's fully conjugated. Each p orbital overlaps with 2 adjacent p orbitals. So this tropylium ion is aromatic in the same way that the cyclopentadienyl anion is aromatic. So we can make salts of the tropylium ion paired up with anions in the same way that we can make salts of the cyclopentadienyl anion paired up with cations. Okay? Any questions about our aromatic ions? Okay, so the next type of aromatic compounds we'll talk about are aromatic heterocycles. A heterocycle, hetero means different, and so a heterocycle is a molecule where at least one of the atoms in the ring is different, meaning that it is not a carbon. So usually it's either a nitrogen, an oxygen, or a sulfur. So we can have rings with either a nitrogen, an oxygen, or a sulfur in them that are aromatic, that still meet all the criteria for aromaticity. One that we've encountered before in the class is pyridine. Okay, this is pyridine. We've used pyridine as a weak base in reactions with thionyl chloride, reactions with phosphorus oxychloride. How many pi electrons are there in pyridine? 6. Okay. We have a lone pair on nitrogen. What kind of orbital is that lone pair residing in? An sp2 hybrid orbital. This is an sp2 hybridized nitrogen. The p orbital is used to make the pi bond. So that means the lone pair is in an sp2 hybrid orbital. So we could draw pyridine in a way where we drew out the p orbitals on each atom in the ring. Okay. And then if we drew the lone pair, that lone pair is going to be in the sp2 hybrid orbital. And what you see is that the lone pair in pyridine is orthogonal to the pi system. It's perpendicular to the pi system. It does not overlap with the pi system. So that lone pair has nothing to do with the pi system. Right, we have 6 pi electrons, 6 atoms in the ring. Lone pair is not part of the pi system. Okay. Here's another aromatic heterocycle. This one is called pyrrole. Okay. How many pi electrons are there in pyrrole? Why 6? How would it be 6? That's the right answer, but we want an explanation. Yes? Okay. So if this nitrogen is sp2 hybridized, normally we'd say, okay, there's 4 groups on that nitrogen. It's going to be sp3 hybridized. However, if this nitrogen is sp2 hybridized, and we put the lone pair in a p orbital, now that p orbital overlaps with the neighboring p orbitals. We now have a fully cyclic, fully conjugated system, and we would have 6 pi electrons, the 4 pi electrons from the double bonds, and this lone pair would also be pi electrons in that case. So, and that in fact is a more stable arrangement than if this nitrogen were to be sp3 hybridized, and that lone pair would not be in a p orbital. So it is in a p orbital because that allows Perol to have a large amount of resonance energy that allows it to be extra stable and have the same stability of many aromatic compounds. So when you have aromatic heterocycles, in some cases, the lone pairs on the heteroatoms are part of the pi system. In other cases, they are not. So you just have to see how many other pi electrons there are and see if you need the lone pair in the pi system for it to be aromatic. So if we draw Perol and we draw our p orbitals, now we do have the lone pair of Perol in one of our p orbitals. So we have 6 pi electrons delocalized across 5 atoms in this case, as opposed to 6. So here we have electrostatic potential maps of pyridine and Perol. We see in pyridine we have a localized red splotch localized on the nitrogen. That is reflective of the fact that the lone pair on that nitrogen is localized as opposed to delocalized. That lone pair resides only on the nitrogen. In contrast with Perol, our red is spread out across the ring, indicating that the lone pair on nitrogen is delocalized along with our other pi electrons. And we have these 6 pi electrons circulating across these 5 atoms, and we have a delocalized system. Okay? So the electrostatic potential maps show us the difference between pyridine and Perol. Now, which of these 2 compounds would be more basic, pyridine or Perol? This would have been a great iClicker question, but we're just asking it as just a general question for you. Which is more basic? They are not equivalent in basicity. I see a few people partially raising their hands. Okay, go ahead. Pyridine is indeed more basic, yes. So if you protonate pyridine, is the conjugate acid aromatic or not? The conjugate acid of pyridine is aromatic because the lone pair is not part of the aromatic pi system. So you protonate that lone pair, the molecule is still aromatic. If you protonate Perol, would the conjugate acid be aromatic? No, it would not. The lone pair is part of the pi system. So if you protonated Perol, you would disrupt the aromatic pi system, and the resulting compound would not be aromatic. Okay? So because the conjugate acid of pyridine is aromatic, the conjugate acid of Perol is not, then pyridine is significantly more basic than Perol. Pyridine is a weak base, but it is still basic. It's basic enough that we use it in many reactions that weak bases are called for, like thionyl chloride reactions and phosphorus oxychloride reactions. Perol itself, you wouldn't consider Perol to be a base at all. You would have to have a super strong acid to be able to protonate Perol because it's really not very basic. Because if you protonate it, you disrupt the aromaticity. Okay, another aromatic heterocycle that occurs commonly in nature is histamine. This molecule right here is histamine. Histamine, when your body secretes it, causes your nose to run, causes your eyes to water and itch. So it is responsible for allergy symptoms. That is why you can take an antihistamine that will block the effects of histamine during allergy seasons. The 5-membered ring with 2 nitrogens, that is known as imidazole. So this molecule here is histamine. If you were to take off this side chain, what you'd be left with is imidazole. So imidazole is the name of the aromatic heterocycle in histamine. How many pi electrons do we have in imidazole? 6. We have 4 coming from the double bonds. We have 2 nitrogens, N1 and N2. This is not IUPAC nomenclature. It would be N1 and N3 if you were using IUPAC, but the book is just distinguishing between the 2 nitrogens. The one the book calls N1, that lone pair is part of the pi system, okay? Because there's no double bond to this nitrogen. So the lone pair is going to be part of the pi system to be in the p orbital. So this nitrogen resembles the nitrogen atom of pyrrole, whereas N2 resembles the nitrogen atom of pyridine in that there is a double bond to that nitrogen, and so the lone pair is in an sp2 hybrid orbital. So would you expect imidazole or histamine to be basic? Is it going to be basic like pyridine or non-basic like pyrrole? Be basic like pyridine, and which nitrogen is going to get protonated? N2 would get protonated, exactly, okay? The imidazole heterocycle is part of the side chain of the amino acid histidine and is present in many proteins. And so when you need a weak base in a biochemical reaction, you often use the imidazole that's part of a histidine side chain for those reactions. So indeed, this is basic, and it protonates on N2, not on N1, okay? So there's lots of heterocycles. We'll draw a few more. I mentioned to you before that my grandfather was an organic chemist. He actually specialized in heterocycles for his research. And he loved heterocycles so much that he, in the 1980s, he had a van and he had a custom paint job done on that van where he had all these aromatic heterocycles painted on the side of his van, okay? So he was very easy to identify when he was driving around. There was only one van in Tampa, Florida in the 1980s with heterocycles painted on the sides, and that belonged to my grandfather. I like heterocycles, but not that much. I do not have any custom paint jobs related to organic chemistry on any of my vehicles. Here's one of the heterocycles he had on his van. This is called pyrimidine. Okay. So pyrimidine looks like pyridine, but with an extra nitrogen. So neither of these nitrogens, neither of the lone pairs on these nitrogens is part of the pi system. And pyrimidine is important because it is one of the components of the bases that are present in DNA and RNA. And then the other aromatic heterocycle that is part of DNA and RNA is known as purine. And it has 4 nitrogens. Okay. Okay, so this is purine. So we have 6 pi electrons, of course, in pyrimidine. The 2 lone pairs are not involved. How many pi electrons in purine? 10, okay? So we have 8 from the double bonds, meaning we need to use the lone pair on this nitrogen. So this nitrogen is like the nitrogen of pyrrole. The other 3 nitrogens are like the nitrogen of pyridine, okay? So pyrimidine and purine make up the 4 bases of DNA. 2 are pyrimidine derivatives, and 2 are purine derivatives. So here they are. Cytosine and thymine, C and T, are the ones based on pyrimidine. Adenine and guanine are the ones based on purine. Okay? But these don't look aromatic. How come these compounds are aromatic? Who can explain? They are. Any ideas? And you'll give you a hint. The book has highlighted in red the electrons that are involved in the pi systems. Okay, so that can give you a hint. We'll start with cytosine. I'd like someone to explain to us why cytosine is aromatic. Okay, Brady? Okay, so this carbon's sp2. So if we sp2 hybridize this nitrogen, then we would have our fully conjugated system of 6 sp2 hybridized atoms. But counting your electrons is going to be tricky because you've got pi electrons here coming out of the ring. So what you want to do is recognize that there is a resonance structure you can draw of cytosine. If we convert this lone pair into a pi bond, and this pi bond into a lone pair on oxygen, we would have a positive charge on nitrogen, negative charge on oxygen. That would be a minor contributor. But it would be an aromatic minor contributor because we would have a double bond here. We would have our 6 pi electrons. Okay? So we have an aromatic resonance structure of cytosine. We have an aromatic resonance structure of thymine. We would do that here and here with both of the amides. Adenine already looks aromatic. We don't have to worry about that. But then in guanine, we would need to draw the aromatic resonance structure. Okay? So because we have aromatic resonance structures of each of these bases, they are indeed aromatic. Now, is their resonance energy as high as benzene? Probably not, but they're still aromatic. They still have this special stability. They're all planar molecules, and because they're planar, the way they orient in DNA allows them to form hydrogen bonding networks that hold the double helical structure together. We're not going to talk about that here because our purpose is talking about aromaticity, but if you look in the book, there's a nice figure that shows you cytosine, hydrogen bonding to guanine, thymine, hydrogen bonding to adenine. The fact that these molecules are planar and aromatic allows them to be oriented perfectly to form those hydrogen bonds in DNA and RNA. Okay, so plenty of aromatic compounds in nature. But now we're going to explain the basis for aromaticity, why molecules with 4n plus 2 pi electrons are aromatic. Why are they more stable than other types of molecules? And then the corollary being, why are molecules with 4n pi electrons extremely unstable? Erich Hückel, a German chemist, discovered this and explained this. And the explanation is rooted in molecular orbital theory. So in chapter 16, we talked about the molecular orbitals of ethylene. We were talking about the pi molecular orbitals. So in a molecule, you can have sigma molecular orbitals and pi molecular orbitals. The sigma bonding molecular orbitals will be very, very low in energy. The sigma star anti-bonding molecular orbitals are very, very high in energy. So we don't really need to worry about those molecular orbitals. We're more interested in what we call the frontier molecular orbitals, the ones that are close to the boundary between bonding and anti-bonding. And those are going to be the pi molecular orbitals. We know that pi electrons are more reactive than sigma electrons. So it's not surprising that pi molecular orbitals, filled pi molecular orbitals, are higher in energy than filled sigma molecular orbitals. And sigma or pi star molecular orbitals are going to be lower in energy than sigma star molecular orbitals. So pi molecular orbitals, a key principle of molecular orbital theory is that the number of molecular orbitals we have is equal to the number of atomic orbitals we used to make those molecular orbitals. So in ethylene, we have 2 p orbitals that are used to make the pi molecular orbitals. So we end up with 2 pi molecular orbitals. A bonding molecular orbital, lower in energy than the original p orbitals. and an antibonding molecular orbital higher in energy by the same amount than those original p orbitals. The relative energies of the molecular orbitals correspond to the number of nodes in those molecular orbitals. Our lowest energy molecular orbital will always have 0 nodes. You see there's no node here. As you go from one carbon to the next, the sign of the lobes of those orbitals are equivalent. Blue on top, red on bottom, right? At BYU, we should be able to understand that. Blue on top of red. Up here, with our antibonding molecular orbital, it has a single node. The node is between the two carbons. As we traverse that node, the sign of the orbital flips. Goes from blue to red, red to blue. Okay? Any questions on our pi molecular orbitals of ethylene? One key thing we note from this is that we have 2 pi electrons in ethylene. They're going to fill the bonding molecular orbital. And that is a lower energy molecular orbital than the p atomic orbitals that were used to create it. Okay? So this reinforces what we learned in chapter 1, which is that bonding is a favorable process, an energetically favorable process. Okay? Now, let's take a look at a more complicated molecule, benzene. Let's look at the molecular orbitals of benzene. We have 6 p orbitals that would be used to make the pi system of benzene. So we need to have 6 molecular orbitals in benzene. Our lowest energy molecular orbital will always have 0 nodes. And another key principle that will help us understand the 4n+2 rule is that there is only one way to have a molecular orbital with 0 nodes. So there will always be only one pi molecular orbital that is lowest in energy. And that's the one right here. As we go around the ring in either direction, around the top it's all blue, around the bottom it's all red, no nodes. So next up, we would have molecular orbitals with 1 node. And there's 2 ways to have 1 node. That node can cut through the center of the ring. All the nodes cut through the center of the ring. But we can cut through the center of the ring and cut through these 2 bonds. So as we cross this node, we go blue to red, blue to red. So that's our node in this particular molecular orbital. We can also have a node cutting through atoms. Over here, the node is cutting through the center of the ring and going through these atoms. When we have a node at an atom, we don't have a lobe there. The probability of finding the electrons at that carbon, if the electrons are in that orbital, is 0. So we don't have a lobe there. So here we have the node here. As we go across the node from top to bottom, it goes red to blue, bottom to top, blue to red. The sign switches as we cross the node. Any questions about how we came up with these 2 molecular orbitals? These are known as degenerate molecular orbitals because they have the same energy. Any molecular orbital or any orbital with the same energy is called a degenerate molecular orbital or degenerate orbital. All right, next up would be molecular orbitals with 2 nodes. Here we have a node cutting through these 2 bonds, similar to what we had here. And we have a node cutting through these 2 atoms. Okay, 2 nodes. Here we have nodes cutting diagonally from here through here and here to here. Okay, so we have 2 nodes cutting diagonally across bonds going through the center of the ring. Okay, and then our highest energy molecular orbital, there's only one way to have 3 nodes, and that is to have those the signs of the orbitals alternate as we go around. Right, blue, red, blue, red, blue, red. So we have a node here, and a node here. Okay, so those are our 6 pi molecular orbitals of benzene. Any questions on how we came up with these orbitals? All right, so we have 6 pi electrons in benzene. Based on Hund's rule, they're going to occupy the lowest energy orbitals. So the first 2 pi electrons go in this orbital. Then we singly populate our degenerate orbitals. So electrons number 3 and 4 will go here and here, and then 5 and 6 will pair up with these. So what you see is if we have 6 pi electrons, we have completely occupied all of our bonding molecular orbitals, and all of our anti-bonding molecular orbitals are unoccupied. So the other thing we do, we draw this line at the energy level of the p orbitals. All of the orbitals below that line are bonding. All of the ones above that line are anti-bonding. So the reason why benzene is so stable is all of its bonding molecular orbitals are fully occupied, and all of its anti-bonding molecular orbitals are empty. Because these orbitals are substantially lower in energy than the p orbitals, the molecule is very stable. There's another thing that's important that we'll come back to when we look at some other molecules, is that something I mentioned before, there's only one molecular orbital that is the lowest in energy. Right? There's only one way to have 0 nodes. So there's always only going to be one molecular orbital at the lowest energy level, but then they're paired up after that. Okay? So there's a shortcut to this where we don't actually draw the molecular orbitals, but we focus on the relative energy levels of the molecular orbitals. For any monocyclic compound that you're wondering if it's aromatic or not, we can put it in what's known as Frost's circle. Frost was a chemist at Northwestern who came up with this idea, also called the inscribed polygon method, where we make a circle and we put our polygon corresponding to our ring inside that circle. And we do so in a manner that there's always one vertex pointing to the bottom. Okay, we always have to have this pointing to the bottom. And then where each vertex intersects the circle, we draw a line, and that line represents the energy level of one of the molecular orbitals. 6 pi molecular orbitals, we have the same energy pattern that we did on the previous slide, 1, 2, 2, 1. Okay? We draw a line through the center of our circle. That's our line between bonding and anti-bonding. If we ended up with orbitals on the line, those would be non-bonding. They would neither contribute to the bonding nor destabilize the bonding. But in benzene, we don't have that. 3 bonding molecular orbitals, 3 anti-bonding molecular orbitals. So this is a shortcut. We don't actually have to know the structure of those benzene molecular orbitals to understand their relative energies. And we fill the 3 bonding molecular orbitals, and we see that benzene is aromatic. Let's look at our aromatic ions. Here's what Frost's circle looks like for cyclopentadienyl anion, and what it looks like for tryptophan cation. In each case, the bonding molecular orbitals are filled, the anti-bonding molecular orbitals are empty. Notice that cyclopentadienyl anion only has 2 anti-bonding molecular orbitals, whereas tryptophan has 4. Okay? What would happen if we had cyclopentadienyl cation? How would these orbitals be filled? Who could describe it to me, to us? How many pi electrons would there be in cyclopentadienyl cation? We've got it right here. There would be 4. Where would those electrons be? Yes, Grace? They're the degenerate ones. They would be each singly occupied, right? So we would have a diradical species. We know radicals are high in energy. Diradicals would be even more high, even much higher in energy than a monoradical. So if we had 4 pi electrons, we'd end up with a diradical, very unstable, right? So that's why compounds with 4n pi electrons are anti-aromatic. They would be diradicals. And the 2 in the 4n plus 2 comes from this lowest energy orbital. And the 4n comes from the fact that after the lowest energy, the molecular orbitals are paired up. And so to fill a level completely, you have to have 4n electrons. Okay? So that's the basis for the 4n plus 2 rule. We can look at another compound that is anti-aromatic, cyclobutadiene. And we see that it has 2 non-bonding molecular orbitals that are singly occupied. Okay, so it would be a diradical. Anti-aromatic compounds are diradicals. Aromatic compounds are not radicals, and their bonding molecular orbitals are fully filled. Okay, the last couple minutes, let's introduce electrophilic aromatic substitution. This is the reaction that is undergone by benzene and other aromatic compounds, the most common reaction. Okay? Benzene does not undergo addition reactions because it would lose its aromaticity. But it does undergo substitutions. It is nucleophilic because pi electrons, we've learned repeatedly, pi electrons are nucleophilic. So the pi electrons of benzene can attack an electrophile. What that gives us is a cyclopentadienyl cation. This is not aromatic. We're losing aromaticity here, but this is resonance stabilized. Okay, we can draw 3 resonance structures of this cation, meaning that we can delocalize the positive charge on 3 different carbons. Okay? So this step is an addition step, but then the second step of the reaction is an elimination. We could draw any of these 3 resonance structures. We can draw the elimination from any of these 3 resonance structures. We just need a base to deprotonate the hydrogen from the carbon where the electrophile ended up being bonded. We deprotonate there. We're eliminating the carbocation, restoring aromaticity, and giving our electrophilic aromatic substitution product and the conjugate acid of the base that we started with. So the good news is all of our electrophilic aromatic substitutions that we're learning in this chapter follow the exact same 2-step mechanism. Okay? And this figure here shows you the 5 different electrophilic aromatic substitutions we're learning in this chapter. The identity of the electrophile is different in each case, so we're going to do different chemistry to generate that electrophile. But once we generate that electrophile, it's going to be these 2 steps, addition and elimination. Which of those 2 steps is going to be the rate determining step? The first one, exactly. We're forming a carbocation. We're also losing aromaticity. So the first step will be slow, the second step will be fast. And this potential energy diagram shows us that, and it shows us the hybrid of that intermediate. We'll stop there. We'll pick up on Friday discussing those specific electrophilic aromatic substitutions.